Classical Physics Tutoring, Chapter 3, Section 2, Wave. This is part 1. Because wave is a big subject, I think it's appropriate to divide into two parts. Now, the wave, you see the wave in the ocean like that, and you wonder what's going on. The water keep coming and receding. Is the water really coming from far away here all the way to the coastline and receding? Is that what the wave is? Well, actually, if you look at the wave underneath, okay, the water is moving like this, the other way around. So when water move up, this part swell up, and when water move down, this part is going to be valley of the wave, okay? And this, the cycling water mass is perfectly synchronized to make a wave. And the shallow area, this circle become more like a ellipsis, okay? So it looks like a wave is moving, but it's a illusion, okay? It's animation. The human eye sees this as moving, the wave coming all the way from here to the coastline. And actually it's not. The water's movement is very local, limited. It just go up and down. But when it's synchronized perfectly, it's look like a moving. So remember, this is animation. Okay? Now, you see when you drop something in the water, it's ripple. Ripple goes out, right? And the ripple moves as if it's moving from center to peripheral. But actually it's not. You can tell if you drop another one, then there is an interference and the ripple go up and down, and it doesn't look like moving anymore, okay? So actually the water movement is just going up and down, but for human eye it's look like this wave is propagating. And for different animal or maybe alien, they see it a different way. But most of the predator, they have the same ability as human. Human is predator too. Something move with synchronous phase. It's like, you know, the prey running around. It's the same thing. It's perceived as movement. So in order to analyze physically, you cannot just use a perception, right? We have to understand that the roots of the perception, why it look like it's moving. And actually some animal or maybe some alien, they don't see it as moving. They just see this part just moving up and down, moving up and down. Although this guy is slightly earlier than this movement, okay? So remember that wave is animation, and I made a video for this. You can find it and watch that video, okay? So what is a wave? Okay, so if you have oscillation at the end of the rope, then this mass move up, right? And this mass move down, but never mass move up already high. So the shape propagate like that. Okay. So now we explained this earlier. This kind of wave, to analyze it, it's easier to use Euler's method, field equation. So what it is this shape f is not only time function but also location and have a maybe phase. This is gonna be the generalized wave equation. So this is like, remember in the fluid dynamics we talk about location and time both, and the stationary becomes only location because the water flow pattern doesn't change. It's not time variant anymore. So we have a time factor and a location factor, and in order to be moving, we have to have at delta t and at delta x location will be exactly same. Means whatever the function, if this is a function f, then it's located delta t time later, it's located at the delta t x, right? So that means we can say this is a condition for wave to propagate. Okay, so delta x, delta t must be n over k, right? And this should be the speed, perceived speed. So this is the root of wave perception. Why it looks like it's moving at the speed v? It's because of this field equation has time variant and location factor, and their relationship is n over k is v. Okay, so if it's you oscillate this end using cosine function, then the wave form becomes something like cosine nt minus x v. Okay, so this is gonna be the wave equation if we oscillate the end of the rope at the cos function. It's gonna be cos omega t, right? Then wave will propagate. So this entire wave is going to be the field equation, and it's not stationary, it has a t in it. So if you look at wave seem to be moving, it's every second. Okay, so that's a basic idea of the wave. And the wave can propagate in both direction. Simply we write negative or positive. So what happens is from here, wave can go this way and other way. Okay. Now, if we expand this equation, what kind of differential equation is going to make the wave? Okay, this solution is often for this differential equation. We look at the 3D wave, right? 3D wave is like you have speaker and make a sounds, right? And that's gonna be this. So the speed square and second derivative is going to be delta square u. So this is going to be the typical wave equation, and in fact this is the way, this is the equation used for electromagnetic EM wave, and even quantum mechanics, the particles wave take this, the similar wave equation. So we can consider that all the physical phenomena, wave phenomena, by analyzing this differential equation, we can pretty much tell what happened to the wave. Okay. Now, some of careful analysis, the wave in the ocean, the scientists created this equation. Basically, it's a sine wave, conveniently very close to sine wave when the water moves up and down below, right? Okay, so this way. Okay, so what happened is this, the wave frequency is the coefficient in front of t is a function of hypertangent. Okay, and for deep sea, kh is larger than 1, so hypertangent is going to be 1. This is going to be the wave speed. The shallow sea, kh is much less than 1, so it's a kh, so v is this. So the ocean wave speeds different depend on the depths. Okay, and this v movement frequency, we can tell the depths of the ocean. So depend on movement, we can tell wave speed, or opposite, by observing wave speed we can tell the depths and other stuff. So I also made another video for this one, so you should look at that one, the application of this wave equation in the ocean. And spherical wave we convert into the polar coordinate. So this is 3D wave become very simple equation. Okay, so remember this, r square is going to be speed square, and you can guess, if you're talking about light speed, this speed c become, the v become c, light speed, right? So that's a wave equation, and the solution, one of the solution is this. So 2 pi f, the frequency, and time minus r over v. Okay, and don't forget the factor r, because when wave propagate in 3D, the wave amplitude attenuate, so by distance a over r. Okay, so when you send a signal to the moon, suppose you send the probe to the moon is 300,000 kilometers away, and the microwave signal is going to attenuate by this function. So it's going to be very, very faint signal. So you have to use a large, high power antenna to send. But the probe flying using a solar cell, and it doesn't have much power. So how can they return the signal to the Earth? It's very faint signal coming from the moon. Okay, so how do you communicate with the probe on the moon? It's going to be a big technical challenge, engineering challenge. Okay, now when you're talking about Ma, it's not easy. Okay, now you're talking about Saturn. It's over a million miles. I mean, it's like, okay, the Mars takes 16 minutes by light, so it's times 16. That's a distance. It's Saturn, I haven't checked, but probably another 100 or so. So communicating with the probe around the Saturn is a major technical challenge. Okay, and I'm not sure if we can do that. If somebody said, yeah, we do that, then I want to see how they do that. Physically, using physics knowledge, it's like almost impossible to do it with some solar cell batteries signal coming all the way back to Earth. It's almost impossible to detect. Okay, you need a lot more high power communication mounted on the probe to communicate with anything around the Saturn. You're talking about edge of the solar system. Forget it. You can never receive the signal from tiny power. Okay, so wave interference. Suppose you have a wave source you put on both source 1 and source 2, and you have wave coming, and there will be an interference. You add this to equation, then the amplitude will be like that, right? Now, equation is wrong here. It should be 1. Now, this, you can tell when two signal overlap. The cos is a difference. The sine, the amplitude go. This increase, but this valley here is going to decrease. Okay, and if frequency is same and just right condition, amplitude can be doubled, and the frequency, the value become all the way negative, doubled. So this is a fairly complicated interference, and this interference happen to almost every wave. Okay, so usually sounds and water. The sounds, they have an experiment is causing this interference properly. Then you can create high pressure point. High pressure point is amplitude is very high in the 3D, and the light sand can float on this high pressure point. The pressure push up the sand, so you see those experiments properly configured speaker is cause interference and create very high power, high pressure sounds point, and a tiny light sand can float or dance around in the air. Okay, so this kind of things is possible. Standing wave is like the music instrument. Why music instrument? I explain to you next, but the standing wave is basically you have a wave going and the bounce here, come back. Okay, so if you can see the wave of the sound, it's look like it's not moving. Even the water, you have a water wave you put the block here, then it's bounce back, and time variant portion is going to disappear if you do it right. So in this equation, let's see. When you add the two wave U1 and U2, right? And in this equation, let's see. Well, you can go through these details. There is a condition that equation, the time variant portion is going to disappear if you add two different frame. And if when it happens, it looks like a wave is standing stationary. And we did that in the fluid dynamics. This time variant portion is gone, so it looks like wave is just standing there, just like the water wave in the fluid dynamics. It's the river water flow and looks like a stationary, nothing changed. Okay, so that's called a standing wave, and it's happening in the music instrument. The reason is harmonic wave. Okay, standing wave happen when two different sounds, and U1 and U2 has a frequency relationship with integer, multiple of integer, means double or 4 times, sometimes 3 times. So integer multiplication, when the sound has this relationship, we call that harmonic wave. They are harmonic, harmony. And you see, harmony is important in the music, because if F1 is slightly larger than F2, then it's create low frequency buzz sounds, and this is very uncomfortable to human ear. Okay, so every music instrument is designed to be multiple each other. When you have a quartet, they initially tune. Why? Because they make sure that frequency here are all harmony. You know, the sounds from 4 music instruments has a harmony. The harmonic means they are all related by the integer value. And even within the guitar, between 2 strings, it's related by harmony. So you know, this music relation is multiplication, right? It's not addition. So the frequencies is increased by logarithmic function, and I made a video for this. You can find it. It's called the perfect marriage of the music and mathematics. Okay, so this harmonic wave is very important, because using Fourier analysis we can tell that if multiple sounds, harmonic sounds, are added up, then it's create one nice clean sound, and that's very comfortable to human ear. Okay, now if one of sound mix is, it's not that multiple of integer, then it's create a lot of buzz sounds overriding. So it's become a mess. This is we can prove this using Fourier analysis. And by the way, I made another video for Fourier analysis. You can learn about it. The Fourier analysis is basically the adding different frequency waves than what you get. That's a kind of analysis. And any kind of the wave function can be broken into multiple simple sine waves or cosine waves, and that's a theory of a Fourier series. Okay, so we have a mathematical tool for certain harmonic sounds. So this is the overview of the wave, and I hope you enjoyed this video, and please move on to the wave 2, part 2. We get into more technical stuff on the web. Okay, if you like, please subscribe.